Good afternoon, everyone. Wake up, Mike. We're getting ready to get started, so hopefully you've had some time to enjoy your lunch, and don't forget about that lovely apple pie sitting in front of you as well. It's actually very tasty. We have a great program for you today. Hopefully you enjoyed your morning. I enjoyed the panels that I attended and participated in. I think we had some really good discussions, and I imagine that mirrored a lot of the other conversations going on around the conference. One reminder for this later today, I just want to remind everyone that the Pickering lecture will be in here from 5:30 to 7 this evening about the Curiosity Mars Science Lab, and as General Titini mentioned yesterday, I believe they're going to be prepared to talk about some of the current science that's coming back from the lab, and I'm looking forward to hearing that myself. But today at lunch, we are going to be talking about a different project. We're going to be talking about NASA's Asteroid Redirect mission, and I would like to introduce the panel moderator, although he's a person that requires no introduction. Bill William Gerstmeyer from NASA. As you all know, he's the Associate Administrator for the Human Exploration Operations Directorate, a very long career at NASA, always in the middle of things that are going on in human spaceflight, and Bill wanted me to keep the introduction short, so I'll stop there so we can get on with the afternoon panel. Bill, it's all yours.
Great. Thank you very much. What we'll do is I'll have a little bit of opening remarks and a video, and then we'll kind of just move down the panel. They'll stay seated. We have a series of charts and presentations we'll talk to you about in terms of the Asteroid Redirect mission. And then I think at the end we'll have a little bit of time for some questions. So continue to enjoy your lunch, but also as you're eating and listening a little bit, think about what you're hearing and see if you can come up with some good questions to talk to us about at the end. I think there's a lot of misconceptions about what the Asteroid Redirect mission is, and I think this is a great forum for us to interact and discuss back and forth and get some of those things clarified and understand where we're heading. So let's see if I can get the first slide here. All right, so, whoops. This is not going right. Okay. So again, the way we'll talk about this is, first of all, Paul will talk to you a little bit about the asteroid observation program, how we're going to find asteroids and what we're doing today currently. That's the first piece. Then Brian will talk a little bit about the robotic mission, which is the capture portion of the asteroid. It's the robotic spacecraft that goes out and captures the object and brings it back to a distant retrograde orbit. Then James will talk to us about the technology that's associated with this, the high-power solar electric propulsion, the new solar arrays. And then Steve will talk about the human exploration piece of this once we've got this object in the distant retrograde orbit. So that's the way we'll go through the talk as we go forward. So with that, I think there's a movie. If we could have that, we'll watch the movie that shows at least the crew piece of the mission. So if I can get the movie. I tell you, our videos are amazing. I think all of us in this audience, though, know that what you saw in that video is not in any way, shape, or form easy to achieve. So our job is to take that video and make it real. Again, I talked to the pieces that we'll talk about here. I won't add much to these. I think I'll turn it over to the experts and let them go through their individual sections. So we'll start with Paul, and he'll talk to us about the observation portion.
I don't have a video like that. That was a great video, really wonderful. Question 1, where does the asteroid come from and how do we get it to orbit the moon? I'm going to talk to you a little bit about NASA's discovery programs. Let's see. Try to go forward here. There we are. NASA is the world leader in searching for asteroids, so we know a few things about how to find them. NEO, I thought I'd give a definition here, near-Earth object, and when I say NEA, as many of us will, it means near-Earth asteroid. So that's just a definition. Those are the objects that can come within the orbit of Mars and get it to within about 1.3 AU, that is 30 million miles of the Earth's orbit. Since 1998, NASA's NEO search programs have found a vast majority of all known NEOs. And including 95% of the 1 kilometer and larger NEOs, which was the prime purpose of this program, to find the hazardous asteroids, those that might hit the Earth, and the large ones, 1 kilometer in size, would be dangerous enough that they could cause a global catastrophe. So those were the first priority of NASA's NEO observations program. Right now we know about 10,000 NEOs. And we're finding them at about 1,000 per year. So we have significant numbers of these asteroids, and the search programs, which you see at the top of the slide, we have the largest performers of NASA's NEO search programs. They're optical telescopes, often much larger than 1 meter in size and larger. The Catalina Sky Survey on the left has found 60% currently of the NEOs. Pan-STARRS in Hawaii has found 30%. Linear, which used to be the main performer, has now shrunk to 3%, but it started in 1998, and it found a great many of the initial large ones. So these are the ways that we find asteroids in general. There are a few others that not listed that would add up to 100%. Okay, let's go again. Oh, I see. So here is a view of the whole process. I just wanted to indicate that at the very top we have discovery and we have initial astrometry, which is measuring the position of the asteroid on the sky. The data gets processed, sent to the Minor Planet Center in Cambridge, Massachusetts. Then it comes to the NEO program office, of which where I work, located at JPL. And the morning after discovery, we will know an initial orbit for an asteroid, and we'll know its rough size. So if the object appears to be interesting, and some of them are more interesting than others, such as a large one that could be headed for the Earth, that one would be very interesting, we screen these objects for interest, and then we will request follow-up astrometry to measure their positions and keep tracking them so that we'll know where they are on the sky. On the second half of this graph, I indicate that a secondary process where we try to physically characterize the asteroid. We look for more orbital tracking. We look for photometry, measure the brightness to get an idea of its size. We look for light curves to get an idea of its rotation rate, colors, its composition. IR spectroscopy is very useful in finding spectral type and getting an idea of the size and the albedo of an asteroid. And on the right at the bottom is radar, and that's a really critical way of finding a lot about asteroids, including their precise orbit, their precise size and rotation rate. So this gives you an idea of the process. Now let's talk about ARM, asteroid redirect targets. These are very special. These are not asteroids that are way out in the asteroid belt. These are asteroids that are much closer to the Earth and in fact have very Earth-like orbits around the Sun, so that their orbital period is about a year, but not exactly. It could be 400 days, it could be less, it could be 280, sorry, it could be 380 days, or some small number of days. The key thing here is that they have to be inclined very little to the ecliptic, that is to say, an Earth-like orbit, same plane as the Earth's orbit, more or less. They have to not cross the Earth's orbit with a huge eccentricity so that they don't zip by the Earth at high velocity. They also need to have a close approach to the Earth in the time frame of the ARM mission. That is to say, we need to be able to redirect it, yes, but the redirection of the asteroid is just a matter of guiding it so that we're going to change its close approach so that it will go near enough to the Moon to be captured into a lunar orbit. So it has to match the schedule that we are targeting towards. We'd like the close approach to be in the early 2020s, so that we, let's say 2023, we get it into orbit around the Moon, and then it takes about a year to get it into this distant retrograde orbit. The size we'd like constrained, 7 to 10 meters, which is 20 to 30 feet. So that's an important requirement, and characterizing the size is a critical point here, and that's why we're going to use radar for this. We'd also like a reasonably slow spin rate, less than 2 RPM. The estimated number of asteroids out there which are suitable for asteroid redirect is in the thousands. 10,000 is one number that I came up with, and we can determine that from the discovery rate of these asteroids in the past. So there are a large number of them, but they are difficult to detect. So we need to augment the search program so that we can find more of these. Right now, we have been finding them at the rate of about 2 to 3 per year. And we have a list of 14 that would be suitable for the asteroid retrieval mission, but these ones were not characterized in size accurately enough when they passed by the Earth in the past, so that many of these are not candidates anymore. We just don't know the size accurately enough. However, 2 of them will be characterized using the Spitzer Space Telescope next year. So we should get a good feeling and be able to constrain the size on those ones quite accurately next year. And another one will come by in 2016. We'll get radar on it, and we should be able to characterize its size then. So we have a good possibility of 3 asteroids on the for asteroid redirect already. And now the idea is that in the future, since we're finding them at 2 to 3 per year when we weren't even looking for them, we should be able to augment that discovery rate and find more of them in the few years we have until we have to select a target. The key thing here is rapid response will be used when possible to characterize the size and spin rate of these asteroids that we find in the next few years. So we need to enhance the discovery capabilities, and I list 3 ways in which we can enhance. First of all, the DARPA Space Surveillance Telescope is a very useful and capable instrument. We'll be testing that on near-Earth objects starting this month, in fact. So the results should be coming in fairly soon. But that telescope is for DoD space situational awareness, so we're not sure whether we can count on a large amount of its time. Enhancing Pan-STARRS-1 and completing Pan-STARRS-2 in Hawaii is something that we can accelerate a little bit, and the next fiscal year the budget is increased so that we will push that and make sure that we can get 100% time on the Pan-STARRS-1 instrument. Right now we're at about 25% time, searching for NEOs. And we will finish and complete the PS2, which should be completed by late 2014. There's also a brand new survey coming online called Atlas, and that is a completely different capability, searching the whole sky every night and looking for moving objects, especially those that are close to the Earth, as ARM targets and candidates often are at the Discovery Pass. That will be completed in early 2015. And there's a picture of that one at the very bottom on the right. With these and other enhancements, we expect that the discovery rate of ARM candidate asteroids will be at least 5 per year. And we have several years now in which to accumulate our list of candidates, so that by the time it's necessary to choose a target, we should have a good number of them. I want to emphasize that though these discovery enhancements also increase the capability for finding hazardous asteroids in general. So the investment that is being put into these discovery assets is not wasted at all. We will be finding more hazardous asteroids and at a faster rate as well. Radar is an essential way of characterizing an asteroid. Goldstone is a 70-meter antenna and is a very capable instrument for measuring the distance to an asteroid within 4 meters. Arecibo can measure distances to 8 meters. On the upper right, you see Bennu, the asteroid target for OSIRIS-REx. The very noisy image is the actual radar image. On the right is a shape model that you can see Bennu, which is about a 500-meter asteroid. On the lower right is what a small arm target might look like. In fact, this one is even smaller. This is a 2-meter asteroid seen in radar. Radar works so that range is vertical, and all of the pixels that you see are all in the same range bin because it's a 2-meter asteroid. There's a spread horizontally, and that's the Doppler shift of the thing because it's rotating. We know that asteroid is only 2 meters in size because we can see what the Doppler shift is. Radar observations can provide the size to within 2 meters. So that it does have the capability of measuring the size accurately enough that we need for characterization. It also provides high precision orbit data and tells us the spin rate. So my final slide, for enhancing characterization assets, we're going to increase the amount of time on radar that's available for NEOs and also streamline the rapid response capabilities of both of these instruments so that we'll be able to get on them as soon as an asteroid is discovered. In fact, we had one last March come by that looked like it was a good arm target. And I said, well, we need to characterize this one right away. And so within 24 hours of discovery, we had we had IRTF observations of it. And within another day, we had radar observations of it. And we had the size characterized essentially within 48 hours. And that asteroid is about 2 to 3 meters in diameter. So it's probably a little small for the intended ARM mission. We'll also augment the IRTF facility in Hawaii, which we'll use to get the spectroscopy so we get an idea of what these asteroids are made of, get their spectral type and thermal signatures. And finally, at the bottom is NEOWISE. NEOWISE is an Earth-orbiting spacecraft that will be scanning in the infrared and searching for asteroids and also characterizing asteroids. That will be reactivated, and the process has started. It's in work, and I believe by December we'll start having observations from NEOWISE. Thank you. I'd like to pass it over to Brian Muirhead.
Green button on top?
Green on top.
Thanks, Paul. NASA seriously started to look at an asteroid redirect mission about 9 months ago. But prior to that, the Keck Institute of Space Studies had looked at the concepts around an asteroid redirect mission and said, there's something here. And we got NASA excited about that. But even before that, there were some clever people that had already been thinking about ways to use solar electric propulsion to rearrange our solar system. And that goes back to 2010. So I'm going to talk about the Asteroid Redirect Robotic Mission. And this is a joint effort of a number of NASA centers, and I have the honor to lead that group. We've been doing an architecture level study. We've been looking at basic architectures and basic design systems that would establish the feasibility of doing this asteroid redirect mission. A key fundamental part of that is solar electric propulsion. It is enabling for doing this class of mission. We've looked at small missions, and Paul talked about that, a lot, small asteroid missions. We've also looked at large asteroid missions, and I'll talk a little bit more about those. When we talk about small, it's a 10-meter class, 1,000 tons. That's still a lot of asteroid. And the large asteroids are much larger, 100-meter class or larger. And we've also looked at the use of these missions to do things associated with planetary defense, and I'll describe that for you as well. All of these architecture studies have been done in the context of key constraints from stakeholders. Things associated with launch dates, launch vehicle performance, launch vehicle options. Affordability is a major driver for all the architecture work we've done. So, as far as small mission targets, we've looked at this particular concept that has evolved from a variety of different options we've looked at. But the objective is to rendezvous with, characterize, capture an asteroid of 10-meter class. And we're doing that inside basically a 15-meter diameter bag. Now, why a bag? The reason we've chosen that technology as opposed to grippers or grappling or some other form is we don't understand the integrity of these bodies. We don't know whether when we touch this body it'll fall apart or not. So the approach of using a bag is very robust in that context. And we found it to be actually a very reasonable way to design these systems. The thing about these objects, though, is we won't know for sure the absolute size or its mass until we get there. We also have uncertainty associated with the spin rate. All of these are factors that we've had to build into the system design to make it robust. You can see there a picture of John Brophy, who was really the original idea guy behind this whole concept, standing next to the levitation mass at the Museum of Contemporary Art in Los Angeles. But that gives you a sense of the scale of what we're trying to work with here. This is the basic mission design. We start with a launch and either on an EELV class vehicle or on a heavy lift, Falcon Heavy or SLS. In the case of an EELV class system, we're going to have to go to LEO and then we're going to spiral out. That'll take us about a year and a half to do that. With the heavy lift, we have the advantage of going direct. We can fly, on a direct trajectory to the target. So on the EELV class, we would use a gravity assist at the moon to get us on our way. We'd be thrusting with our solar electric propulsion basically for a year and a half to get to the rendezvous point at the asteroid's orbit. As we approach, we'll be using our onboard cameras to do optical navigation to see the target and maneuver to the target. Once we're at the target, we'll characterize the target using optical and LiDAR capabilities, and then we'll decide exactly how we're going to approach it. And basically, we stand off from the asteroid and we slowly fly around it. At the point where we now have enveloped the asteroid, we engage the capture mechanism. And that mechanism basically grabs the asteroid rather quickly, and we deal with all the dynamics associated with that through the capture mechanism. So depending on what the spin rate and spin state is, the capture mechanism will basically protect the spacecraft. Once we've grabbed the asteroid, we'll despin it, and once we've despun it, we basically bring it close to the spacecraft, and now we're ready to return to the cislunar space. So for roughly the next 3 years, we would be thrusting and targeting. We would be only applying on the order of 150 meters per second to this rather large body. But that's enough to change its trajectory and timing such that we can fly by the moon and get a lunar gravity assist of the order of a couple kilometers a second, which is enough to get us into lunar orbit. And we've chosen a distant retrograde orbit because it's a very stable orbit and one we know that a crewed mission can access. So that's the basic overall mission design. And we can apply this to pretty much any target, and we've applied it to a number of targets. The target we've been focusing on to date has been 2009 BD. It'll be coming back in June of 2023. Other targets could come back sooner or later. But for this class of mission, we're coming back when the asteroid's coming back. And our job is to divert it just enough to get it into lunar orbit. For the large asteroid missions, these are very different. Now, these are bodies, as Paul said, there's a lot less of them, but they're more easily identified. The key to these is finding something on the surface that we can actually pick up. And we're thinking of boulders, and they need to be of a size, of a class on the order of about 20 meters. I'm sorry, about 2 meters, about 20 tons. Because in this case, we're bringing the object back. So we're providing all the delta V to bring it back. And so that's why we're limited in the mass. And the real challenge is figuring out where those boulders are and how we can safely retrieve them. There's a great example target right now called Itokawa. Hayabusa was there. We've got high-resolution imaging of the surface of Itokawa. We're going to look closely to see whether there are representative boulders on Itokawa. If we see them there, then there's a chance they're going to be other places. And so this is a very, it has a great potential to be a very different kind of mission. We've also got ideas where we could do a mission like this and maybe even bring back an individual asteroid as well. Here again, though, we're looking at the orbit characteristics of these bodies, and we'll, like I said, be limited by the size and mass of the object we can bring back. So again, these large asteroids, small asteroid options are things we're going to be looking at much more closely over the next few months to try to converge on an overall mission objective that will satisfy the key stakeholders. Here's our flight system. This flight system is dominated by the solar electric propulsion system. We're going to carry roughly 10 tons of xenon, Compare that to Dawn. Dawn carries 400 kilograms of xenon, but that's the size system that we need to build and fly. We're going to use Hall thrusters, high performance 3,000 second Hall thrusters, long life. These are systems that are going to be burning for basically on the order of 5 years. On top of that SEP stage is the mission module. This is a high heritage, deep space, more or less build-to-print avionics system. And on top of that is really where the new invention is. It's the capture system. Is it a capture bag? Is it a capture grapple system? Whatever it is we're going to use to grab a piece of asteroid or a whole asteroid, that's the most unique invention whose problems we have to solve. The work we've done up to date has been focused around, like I said, architecture and system design. We've been looking for technical and programmatic feasibility. And what we've found is what we believe is a very versatile and very robust set of options, a set of tools that we can put together to not only do the redirect mission, but also to do a planetary defense demonstration if NASA wants to do that. We can do science missions, and obviously we're about doing exploration missions. So the technologies that we've been focusing on, the SEP, mission design, the proximity operations, are all affordable steps toward a future that includes exploration, both of potential exploration of the Moon and Mars. Thank you very much.
All right. I'm represented the Space Technology Mission Directorate, and I'm going to talk a little bit more about the technologies and specifically SEP. So from a Space Technology Mission Directorate standpoint, our perspective is that we recognize that solar electric propulsion, and specifically high-powered solar electric propulsion, is something that multiple agencies, the commercial sector, and certainly NASA has a strong interest in developing for the future. And so I'll talk a little bit about the uses of it and what specifically we're going to do for the asteroid mission. In the case of the asteroid mission, there are some main components that make up the high-powered solar electric propulsion capability. There's the solar arrays themselves. The actual photovoltaic cells are not too different than the most advanced photovoltaic cells that are on commercial satellites today. But how we deploy those and how we put them together in a solar array is significantly different. We have two different approaches. You could think of this as an oriental fan approach where you have a circular ring, or you have these rectangular arrays that roll out. In each case, the structure is quite different compared to the flat panel arrays that are traditionally used on spacecraft like Dawn as well as on commercial spacecraft. And it's that difference in how we structurally hold on to and how we gang together all the photovoltaic cells that is a big difference. We have essentially a factor of 2 reduction in the overall mass and a factor of 3 reduction in the packing volume for these solar arrays relative to arrays that we are flying today on commercial spacecraft and advanced science spacecraft. And that difference is something that needs to be done in order for us to be able to extend solar electric propulsion to 50 kilowatts or 100 kilowatts or even higher. Without that kind of solar array technology, we would not be able to actually do that because the current array technology is limited by shroud sizes and the overall mass of the systems and the extendability of being able to modularly expand to larger array sizes. So one of the big technology demos will be the actual new array structures. Of course, as Brian pointed out, we're using advanced Hall thrusters. These Hall thrusters will be different in several respects than Hall thrusters that are operational and flying today. We will have a higher thrust capability with them. They will have a proven longer life capability, so we can in fact operate them over a 5-year period reliably and sustainably relative to current thrust capability, and we're actually pushing the ISP of the Hall thrusters up to about 3,000 seconds as opposed to the standard, which is around 2,000 seconds today. All of those pushes in technology capability of the Hall thrusters is really what both the commercial market as well as the human exploration side are really looking towards that kind of capability for their future missions. So it's a very important piece of it. The PPUs, or power processing units, that go along with those thrusters are also a technology push that we're taking into account. And the final piece, of course, is all that xenon. In Brian's diagram, he showed you that actually a substantial portion of this overall mission is 10 tons of xenon that we have to carry around. Pushing that much propellant, xenon propellant, through the Hall thrusters over a 5-year period of time, of course, is something that we haven't even come close to doing, but it is, of course, the kind of capability that we will need if we want to get serious about using high-powered solar electric propulsion for deep space human exploration. If you look at the uses for high-powered solar electric propulsion, they're pretty significant. If you really want to get serious about doing orbital debris mitigation, the agency or the nation wants to participate maybe even internationally in that. In order to get the delta V to be able to go to multiple spacecraft and impart that delta V to deorbit them, solar electric propulsion is one of the most efficient ways to get that delta V. Of course, there are science missions where you want to go outside of the ecliptic plane, and just like the ARM mission, solar electric propulsion is essentially enabling for those kinds of missions. Specifically for ARM, we looked at, well, what would it take to do ARM from a chemical propulsion standpoint? First of all, we would have to have either high performance chemical propulsion that is storable over a long period of time so that we could do burns when on the way back as well as just on the departure stage. And it looks like we would have to have 2 or even 3 heavy lift launches in order to enable a single ARM mission, while we could easily do the ARM mission using high-powered solar electric propulsion with just an Atlas 5 class mission if that's where the launch vehicle was restricted to. In other words, with solar electric propulsion, the ARM mission is doable, it's viable, it's a reasonable mission that we could consider that is affordable. Without it, it essentially is not possible to do the asteroid retrieval mission. There are similarly other science missions that fell into that same category, especially those that are looking for data outside of the ecliptic plane. To get there chemically is either challenging or unachievable. And so we're looking towards using these capabilities in the future. Of course, there are many other applications for high-powered solar electric propulsion, but one of the main threads from a NASA perspective is to use the high-powered solar electric propulsion for future deep space exploration missions. While we may not think of solar electric propulsion as a fast transit, so if you're thinking about sending people to Mars, you probably will not use solar electric propulsion as your main propulsion system to take you there and back, because it would take a year or maybe 2 years to get to Mars using solar electric propulsion. But to stage the cargo that you need and the logistics that you need and potentially your transportation propellant to get back from Mars, you could use solar electric propulsion and cut the overall mass of a human mission to Mars by at least a factor of 2, if not a factor of 3, just by using the solar electric propulsion to stage all the logistics and stage all the equipment at Mars and send the crew there in a chemical propulsion stage. And that translates into an enormous affordability issue that of course we're looking at, and that is the driver for looking at solar electric propulsion as a portion of our transportation architecture for human exploration. If you look at how solar electric propulsion that we would do for ARM fits into the overall strategy for solar electric propulsion, over the long haul. Of course, solar electric propulsion is nothing new. Many commercial communication satellites in geo orbit today use solar electric propulsion for station keeping. If you look back to AHEF, it actually had a problem with its chemical kick stage to change it from GTO to geostationary orbit, and they used the backup system, which was not really intended to do it, used their solar electric propulsion system to actually get them to their correct geo orbit. And that happened in 2010. Dawn, which started in 2007, has had a very successful asteroid observation mission strategy where they've actually they're going to their second asteroid today. You know, again, you could not have even think of doing the Dawn mission if it weren't for solar electric propulsion, and that is at a lower power level. So it's nothing new that we have actually had solar electric propulsion, but when you jump from about the 15 to 20 kilowatt range to the next level up, 50 kilowatts or beyond, there's actually a lot of new technologies that need to be brought in to allow that to occur. And really, the Space Technology Mission Directorate is trying to partner with the Science Mission Directorate and the Human Exploration Mission Directorate on this ideal mission where we could leverage the investments that we were already going to make in solar propulsion demonstration and use them in this context for the ARM mission. And you could see that we're taking the next steps. We're up to about 50 kilowatts of total power, and we're going to have 4 10 to 12 kilowatt Hall thrusters to actually push that xenon, that 10 metric tons of xenon through the system. And you could see that this, the technologies that we would actually use here are modular in the sense that they would quickly extend our ability to say, okay, now we know how to build a 300 kilowatt solar electric propulsion vehicle that would do the deep space exploration and stage the equipment for future human exploration. And I think I will hand it over to Steve at this point.
Thanks, James. Steve Stitch from the Johnson Space Center. I've had the privilege of leading a team at JSC that's been looking at all kinds of various missions really for the last 2 years, trying to decide what's the best use of SLS and Orion for these early missions once we get the capability built. And we've had great partnerships with JPL, with KSC, Marshall, Langley, Glenn, all looking at what's the best kind of mission we can go put together. And when you look at the smorgasbord of things we could go do, I think this asteroid mission is a really incredible mission. If you think about where we'll be in the 2021, 2023 timeframe when we do this mission, it will have been 50 years since we went to the moon in 1972 with Apollo. And we've done many, many great things in space with the International Space Station, which we continue to do today, with Space Shuttle, which I was a large part of. When you think about what America's about, what our space program ought to be about, it ought to be about doing bold missions. And we look at this mission, and you think about we're going to send 2 crew out further than they've ever been in space. We're going to send them out into the Orion spacecraft. We're going to depressurize that spacecraft and execute a couple spacewalks to get samples from an asteroid that we've moved to this spot. We've moved a body in the solar system to this spot in cislunar space. You know, it's a pretty bold, ambitious mission with only the Orion vehicle being there for the crew to depend upon. So I want you to just think about that, and when you think about what you saw in the video, think about this as a very bold mission. So talk a little bit about how we're going to execute the mission. As you saw in the video, it's some pretty impressive trajectory operations. We're going out to this orbit we call a distant retrograde orbit. It's kind of balanced by the gravitational forces between the Earth and the Moon. It's a very stable orbit. We can put the asteroid in this orbit. And we selected it uniquely because we can get there with Orion in the initial configuration, and then we can also robotically bring that asteroid to this orbit. It takes about 9 days to traverse out from the Earth to the asteroid, and you can see the Moon kind of in the center of the slide. We'll execute a lunar gravity assist, which you saw in the video. We've done that a lot on our planetary missions. We have not done that in human spaceflight. It'll be a pretty bold maneuver, but we need that to insert ourselves into this distant retrograde orbit. We'll spend about 5 days in this blue DRO. You can see that the dotted line is where the asteroid was in the DRO trajectory before we got there. And then we'll do 2 spacewalks while we're in this distant retrograde orbit. We've done a lot of contingency planning already at a stage that I would say is atypical for early development. We've looked at, for example, all the burns that you see here, the TLI to get us out to the moon, the lunar gravity assist on the outbound and inbound legs, and then the DRO departure burn. We've looked at all those burns, and we can execute those burns and still bring the crew home safely in the event that the Orion service module engine fails. So we've done a lot of planning, even though it's a very complicated trajectory. It's something we need to learn how to do in human spaceflight. You can see there's a lunar gravity assist also on the way back to Earth, and the return flight time is 11 days. So if you think about where we've been lately in human spaceflight, we have the luxury of, on the International Space Station, or even Space Shuttle, coming home in a matter of hours or a matter of a day or two. Now with this mission, we're starting to step out into cislunar space, into an area we're going to have to embark on to someday go to Mars. So we're pushing the boundary a little bit in terms of risk, understanding how we can return, understanding how we manage contingencies. But once we execute the TLI burn, we're embarking on a pretty long mission with only Orion there to serve as the support system for the crew. We'll talk a little bit about our philosophy. James did a wonderful job of talking about all the unique technologies that the Space Technology Mission Directorate is building for this mission. I would say in the human spaceflight side, we've approached this mission from an anti-technology perspective. We're looking at it from what can we do with the hardware that we've built today. Well, let's leverage on the things that we've used in the past. And we've tried to build a series of mission kits to put into Orion. We'll let the Orion team continue to make great progress toward EFT-1 in 2014, early next year, and then the first uncrewed mission in 2017. And then we'll install kits to minimize changes to Orion to go execute this mission. The first thing that we've done in the top of the slide, as you can see from a spacesuit perspective, we've looked at the shuttle modified ACES, which is really a derivative from the Gemini spacesuit that was used many, many years ago. And we think we can modify that suit. We can add a little flexible bearing in the elbow to provide a little bit more ability for the crew to do the task of taking the samples from the asteroid. And we add some MLI garments, just like a typical spacesuit would have. We install a PLIS system, which we're working on under Advanced Exploration Systems today. We're in that system. We're leveraging technology from Orion, a recyclable amine swing bed, and a fan pump that's in the Orion suit loop. And so we would build this system largely out of existing parts. Today, we've already done 5 tests in the NBL of how can the crew perform. The biggest concern with the suit is using this modified ACES technology is can the crew really do those tasks? They've done a couple of 2-hour training exercises in the neutral buoyancy lab, and this month we're working up to maybe 4-hour capabilities to try to understand, can we really go use this suit to do these tasks? So we're trying to be innovative, we're trying to be affordable, and trying to drive down cost. You can see our translation aids is very simple. We've taken a page from the Russians. The Russians use a very simple boom system called Strela. So we would use a boom system for the crew to go across from Orion to the asteroid redirect vehicle and also to position themselves for the EVA task. The comm kit we're using is a derivative of what we're using on Orion, so we'll have communications between the robotic ARV spacecraft and Orion. And then you might wonder, well, how are you going to do the represses in Orion? It wasn't designed for multiple EVAs, but it has the contingency EVA capability built in. It was designed for the crew to survive for 144 hours in a depressed state. Well, that was a wonderful design. And when you look at the capabilities of Orion, we're able to now take that capability of being able to depress Orion, and we use a simple repress kit with air that we install in Orion. And when the crew comes back in from the EVA, they just open a valve in the repress kit, and then we can repress with air as a simple atmosphere. And that's a little bit of another page from the Russians. So we're trying to be very affordable, and when you look at what those who envisioned Orion did, they really built this perfect spacecraft for this mission. Again, when we look at some of the hardware we're using, we studied grapple versus docking. Should I grapple this robotic spacecraft that has the asteroid, or should I go ahead and dock to it? We did a trade study. It was a little more massive to go ahead and use the docking system. What we're using is the International Space Station derived International Docking System standard. And if you look at where we're going to need to go in exploration, we're going to be docking a lot of components for the long term, so it was a much better decision to go with the docking system. Also, much like we did for shuttle Mir and shuttle station, sometimes the shuttle controlled the stack, sometimes the space station does. Again, here we were able to use Orion to actually maneuver the stack. We need to do that in a couple cases for the EVA, and the docking system was able to provide enough load authority to allow the Orion jets to fire and maneuver the vehicle. And then we're using the navigation system in Orion. It's already been tested on shuttle. It's a system called Storm. It's a flash LiDAR system and a camera system, and so we would install that in the hatch, and we would use that for the rendezvous system. The video probably did a much better job of explaining the EVAs than I can do in the graphic. What we're looking at is 2 crew members on the flight. Just from a mass perspective, it was better to optimize with 2 crew. We would do 2 short duration 4-hour EVAs to go out and collect the samples. We would traverse across using that boom that was well described in the video, and then go get a couple samples. And probably the most challenging task will be getting through the bag material. We think we can either cut through it or have some little slits built in the bag to go ahead and collect the samples. And so we've got this EVA capability that we've already been working on. And then we've worked hand in hand with to look at how do we modify the robotic spacecraft to accommodate EVA. You can see we have 85 kilograms of tools that we pre-stow on the spacecraft, much like we pre-stow tools on the International Space Station for shuttle spacewalks. Again, we have a couple booms that we've stowed on the spacecraft, and then we have handrails. You can see the docking system on the back part of the spacecraft. So we've pre-staged a bunch of things to allow the crew to have easy access on the spacecraft. We've been working hand in hand with Brian and his team to lay all this hardware out. And then we've been working very hard to think about how does this mission feed forward to Mars. And if you look at the chart, on the bottom part, we're doing a lot of things very innovatively on the space station to prepare for exploration. We're doing assembly operations, sometimes autonomous on the space station, and that's important as we feed forward to Mars. And so what you see on this chart is the kind of things we need to have to execute a Mars mission in the horizontal rows, and then in the vertical columns, you can see the different kinds of missions, anywhere from the current ISS hops to a long surface stay on Mars. So what we're trying to do is build up capabilities to eventually get to Mars. And so you see early on, we're doing a lot of things on space station today with deep space habitats, learning how to live and work in space. High reliability life support, we continue to evolve those systems on space station. So we continue to need that as we move forward to Mars. I could probably put a lot of human research on here that we're doing on station to understand how crews live and work in space. And then we kind of add the building blocks that you get with the Asteroid redirect mission. The first piece of that being the heavy lift launch capability that SLS gives us, which we absolutely have to execute any Mars mission. And then the Orion capability, obviously, as not only we use it for this mission in order for the crew to live and work, but also for the ascent and return. And then we continue to build upon that. We add the navigation capability in deep space with this mission, which we'll need all the way to Mars. We begin to add those other capabilities, slow electric propulsion, which James talked about for cargo. And so we see this mission as sort of building these stepping stones to Mars. And then later on, we'll need the more advanced capability of entry, descent, and landing, surface power, surface habitats. But this is the starting point, and it's a little bit of an evolution, just like we did with our early space program. And then we've been also thinking about other destinations relative to the GER, and these are some thought provokers. These are some notional concepts of what we might do after this mission. We see this as one mission in a series of missions. We could obviously add a habitat, maybe an international module. You see a commercial module on the left-hand slide where we might exploit the asteroid a little bit more. And then in terms of the GER, there's multiple paths to deep space to Mars and then toward lunar missions. And you see concepts here where we might use that initial spacecraft to either spiral down to low lunar orbit and execute lunar missions or deep space missions. And so these are just some thought provokers we've been studying. And that's all I had, and thank you very much, and look forward to your questions.
Thanks. I think we have some time for some questions, if we could have those. See, I guess we'll start over there. If you get a mic, somebody give him a mic.
Hi. How much unity is there within the NASA organization that this is the right mission to do?
So I guess the question was, how much unity is there in the NASA organization that this is the right mission to do? I would tell you across this group on the stage, there's 100% agreement. And I would say also across the agency, I think there's pretty strong support for this mission. I think the thing that's important is sometimes we think of this as, or it may get characterized as just a mission or a destination. And that's kind of the wrong way of thinking of this. If you look at Steve's chart that he showed, the stair-step chart, we see this as a way that we can take the capability we have with Orion and SLS and we can advance it and moving forward. We can use this mission to push the solar electric propulsion in a meaningful way. It can improve our observation campaign for the potentially hazardous Earth asteroids. So when you look at all those things, it does something that helps every one of the activities we're moving forward, and it helps them move forward in a real and meaningful way. So in that sense, I think there's a pretty strong consensus that this is something we can do. The other aspect is affordability. In terms of this mission, it doesn't require very much new hardware. It uses Orion and SLS as they're being designed. There's the kits that Steve talked about. It pushes a little bit on robotic spacecraft. The capture stuff is a little bit new. But in terms of real content add, it's not that much, and it's also fairly soon in the time scales that we're talking about. The 2023 time frame is driven primarily by finding an object to get it there, but that's about the right time when the capability's there. So I'll see if the panelists have anything else they'd like to add to that response. Okay, they're trained well.
Perfect.
All right, so any other questions? Yep. Yeah, maybe we can get a mic, somebody?
Maybe you can hear me okay?
No, hang on a minute. We're having people run, this is exciting.
Sorry, okay, thanks.
As long as they don't carry scissors, we're okay. Go ahead.
That's all right, having her run to me is okay. This will be the first flight of Orion with crew, and so in a way it's a test flight, and I know that that's something that could be debated elsewhere, but since it will be the first flight, what will be the capability of the mission to be aborted and get the crew back safely and abandon the other mission? What will be the maximum time that they'll be away from a safe return to Earth?
Okay. Steve, you want to answer that?
Yeah, if I can get my mic. Is my mic on? Okay, good. Yeah, we've looked at, Frank, all the different cases for, starting with that first burn, the translunar injection, and the worst case that we looked at for this particular launch epoch was the DRO. When we insert into that distant retrograde orbit, it would take 2 burns to come back if the main engine would fail, and that would take about 27 days to get back. We're still talking about, when's the right time to fly this mission? Is it EM2 or EM3? You might think, with a brand new spacecraft, you might want to take a little less ambitious mission. But at some point, we're going to have to venture out to these kind of durations. When I look at Mars, those Mars transit times are 6 to 9 months. And so somehow we've got to get past this paradigm of I can come home in, hours or days versus it might take me 10 days. And so, the way we look at this mission is this is kind of a stepping stone in that direction. When you're on the way to Mars, there's some places where it may take months to come home. And so, but we think it's pretty manageable. We'll have checked out, Orion on maybe the first mission, an EM2 type mission. And then we'll have obviously tested all the systems on the ground pretty well. So, and then we'll spend a couple orbits about the Earth before we execute the TLI, just like we did in Apollo. So, hopefully that answers your question.
And I think the other thing I would add is also I think we think of this as separable activities. So if for some reason the asteroid doesn't get there until 2023 or 2025, and we are ready to go fly EM2 on 2021 timeframe as we are today, we would go fly EM2 first, and then we would pick this mission up second. So we're not going to hold off on the development of Orion and SLS to match when the asteroid can be in this location. We're going to continue with Orion and SLS on the pace that we can get them ready to go fly and then go do this mission. So we'll also get a pretty good chance to check out a lot of the systems on EM1 when we do it uncrewed. We're talking about doing this distant retrograde orbit, almost exactly what you've seen here in these concepts. So we'll get a chance to make sure all the burn sequences, all the lunar gravity assist, all the orbital mechanics aspects will be there. Some of the life support stuff we believe we can test sufficiently enough on the ground to make sure, based on our space station experience, that we have enough capability and enough robustness in those systems to support what we want to go do here. So again, I think we have a measured approach, but I think the thing to think about it is it's not all linked serially. We can do pieces and break it up as it's needed. All right. Yep.
Yes, hello. Ken Washington, Lockheed Martin. I think most of us in this room are pretty excited, and the enthusiasm is building. But I think to build a kind of global and broad base of enthusiasm and support, we need to get the children and America talking about this. So, and my sense is that the dialogue there's not yet a buzz about the mission like we would like to see. So could you talk a little bit about some of the activities and plans that you have to create a more global buzz about this mission, so we can begin to get our young people and other folks who don't work in the business like we in this room do, talking about this mission and getting excited about it?
Man, they all look over here. This is not a good sign.
Well, one thing I can tell you that we've started some of the social media activities. We've done a Google Hangout activity. We did what was the Ask Me Anything on Reddit. We got a number of scientists and engineers. It was really, we had hundreds of questions that we answered over the course of a couple of hours. And there's a lot more of those kind of opportunities I think we can use, because people really, like you say, people are excited about this. It's a very novel, bold idea, and they'd like to hear more about it.
Yeah, I think we're also having a workshop. We'll talk about it at the end. We'll have another workshop at the end of September at the Lunar Planetary Institute in Houston, and so we'll try to get a little bit more support at that time. We're using some innovative media techniques at that workshop as well to try to reach out to as many people as we can. Of course, we released a little bit more information. The video's out on the web, and we continue to try to reach out to people on the NASA website under the Asteroid Initiative block as well.
And we did a request for information activity where we reached out to essentially anyone to see who would be interested in this mission, and we received about 400 responses to that RFI, which was a pretty astounding number of responses. The majority of those came from individuals, folks with ideas. So we've down selected out of those about 96, I think, different things will be discussed at this workshop that Steve talked about. So I think we're reaching out very strongly. We'll do a press event today at 3 o'clock with folks to talk a little bit about this mission. But I think probably more importantly, each one of you in this room ought to think about what you saw in the video. We gave you an idea technically of what it means, and now you got to take that technically how the mission comes together and describe it in maybe a little softer terms that you can relate to your friends that are not in the aerospace industry. And we ought to start talking about this as something that's pretty exciting. And again, I think the thing that's important is don't get hung up on so much as this is a particular mission and this is a particular asteroid. Think of this as really pushing human presence into deep space beyond low Earth orbit that enables lunar activities potentially in the future. It also enables the Mars activities, as Steve's chart said. This is a way for us to start breaking the tie and get out of low Earth orbit. And it's a pretty compelling mission, I think, if we look at it that way. But it's best if you articulate it in your own way to the community and the groups of folks you talk to every day. Another question out there?
In the back.
Okay, go ahead in the back.
All right, I have the microphone. So,
yep.
This is Chris Lewicki from Planetary Resources, and Mr. Gerstenmaier, I think this question is for you. And it's building off what you just mentioned, with creating a capability to take humans deeper into space, more sustainably, and for longer periods of time. We're making a tremendous investment in a capability to get there and a capability to bring something to visit. Would you see opportunities for actually doing either of these things more than once? Either bringing more objects, we have a capability to go get large things in space, to continue to bring them back to a hub orbiting the moon, or even the opportunity to make multiple visits with human-tended operations for development of experiments for in-situ resource utilization and other topics?
My answer to that would be yes. I mean, if you look at what we talk about when we talk about capability-driven, everything we build feeds forward into something else. So this robotic spacecraft, it could be used again to reposition habitation modules. The capture device could be used to grab other objects, bring them in. The other thing that this distant retrograde orbit brings us is it's an extremely stable orbit. The object will stay there without any propulsion for roughly 100 years or more. So I don't think we'll get as much out of this object in the one activity that we will do here with the crew to fully understand and explore this asteroid. So it would be available for companies like yours and others to go use this as a demonstration, to look at techniques, other things. So this is a piece that builds and allows others to go interact with and move forward. So I think, as you described, it clearly is a piece of something that can be used in a multitude of ways, and it's up to us to be imaginative and creative about how we can use this object, because I think we'll learn a lot about this object. Bringing the crew there, I think, also brings a unique aspect. You know, they can survey the surface, look for differences in the surface. Some of these may be more rubble piles, and it may be in the bag as a rubble pile. But having the crew there, they can deal with the unknowns of what's associated with this object in a much better way than a robotic activity could. And then that will really enhance our knowledge of what these asteroids are. They'll help you in terms of planetary resources to understand how these things are put together, what potential sources may be there, what minerals, as you described earlier this morning, may be there. I think it really starts the discussion to where this becomes real. So this is, again, in the collaborative spirit, this is a good thing between the government and the private side to kind of work together for this mission.
I'd just like to add that this is a new frontier. These small asteroids are really a new frontier. And Chris, I know you're particularly interested in these small ones. There are many, many more small ones than big ones, and we don't really know what the small ones look like. We don't know their internal strength. We don't really know how well they're held together. There's a wide variety of spectral types, compositions, so there's a lot to learn about these small ones. And to bring back one and put it into orbit around the moon and study it up close and to understand its properties, bulk properties, is really important, I think, and it'll open up doors to further exploitation of asteroids.
Right. Yep.
Yeah, we heard a lot about the Global Exploration Roadmap. Could you maybe expand a bit about discussions potentially with international partners? Is that in the frame?
Yeah, the question was again about the Global Exploration Roadmap. You'll see in the Global Exploration Roadmap, asteroids are talked about as a activity in the framework or in the roadmap. We're going to have the international partners come to the workshop in September. They will talk about their interest in asteroids. We know that the Japanese have been very interested in the asteroids with Hayabusa and in Hayabusa 2. So we expect quite a bit of activity from JAXA. I think other countries are interested, potentially some more in lunar activities, but again, we're in cislunar space with this vehicle. Are there things we could do that help with some of the activities they have planned on the surface of the moon? It turns out we've been looking again at this region and this distant retrograde orbit. Depending on exactly what orbit you circle the moon at, you may have 4 or 5 continuous days of communication with the south pole of the moon. So that would potentially allow us on a subsequent mission to go with an Orion capsule and telerobotically, with a short time delay, command a robot in the south pole of the moon. And there may be a lot of interest in the international community to do some robotic activities on the surface of the moon. So again, I think the thing is, don't get so limited in your thinking that this is just one mission, one piece. Think of it in the broader sense of what capabilities it's enabling. Think about how the the partners and other folks and commercial companies can use this to their benefits.
And when we look at the implementation of the hardware, there's opportunities for international partnerships as well as, of course, working closely with industry.
And I would add, we went to the docking system specifically for extensibility, specifically to look at, what can we do with this in subsequent missions. So we've been focused a lot on this first mission, but putting a docking system on there, if you want to add some kind of either commercial or international partner habitat to do extra missions on the asteroid, or as Bill said, enable other parts of the global exploration roadmap, we think we've kind of enabled that by going with the docking system.
Okay. Yep. In the back there?
Yeah, my name is Jim Martin. My initial question was, when you're done with this asteroid, what do you intend to do with it? And that led me to the request, when you're done with it, can I have it?
So we've talked about what to do. Once we have it in the distant retrograde orbit, it allows a lot of options. We could continue to go back to it either with government funded flights. We could let Chris and his industry go to exploit the asteroid. So we think we have a lot of options. We haven't really talked in detail about all those kind of things that we could go do, but certainly we've enabled, by the way we've designed this mission, for multiple visits to the asteroid.
From a safety point of view, the asteroid will be safe for 100 years, so you can be comfortable that it will stay in this orbit for 100 years or so. But if that is not enough, I think that once you're finished with it and you have no further need of it, send it in to impact the moon. That would make sense to me.
All right. Any other questions? Yep. What?
Yes, sir. You said as part of looking for asteroids that we were looking for targets, that we were finding possibly dangerous ones, and we're just wondering if what's going to be done with that information, or would we send probes to those to figure out if they are dangerous or what, or what's being done with that info that you're collecting?
So NASA's Near Earth Object Program Office, that's its main purpose, is to keep track of and find as many as possible of the hazardous asteroids. We have, and asteroids are discovered nightly. I mean, last week we had a really prolific night. We had 20 asteroids, near Earth asteroids found, for example. Those asteroids then go into our database. They're posted on our website. We compute the calculate whether or not it can hit the Earth in the next 100 years, and that sort of thing. So the data itself is online, and the analyses of whether it can hit the Earth, for example, is online. And there are no really hazardous asteroids out there right now. Apophis was one for a while. As we continue to track them, then we can eliminate the possibility that it could hit the Earth. So that much is something, and these data and numbers are updated nightly.
And what I talked about briefly was the possibility of doing a planetary defense demonstration, yeah. The ability to actually apply force to an asteroid body and change its trajectory in a measurable way, and know that in fact we can do that. Like as Paul said, there's no hazardous asteroid we'd be going to today, but we could certainly demonstrate the capability to do at least a couple of different types of planetary defense maneuver.
All right. Yep. Go ahead.
As it was shown, your asteroid was all nicely tied up. I assume, or I hope, that you're going to design the capture mechanism so you can unravel it. Otherwise, many of the things you're talking about and exploring it would be very, very difficult to do.
The details of how the bag will be explored, how we will open it up, are things that we're just starting to work on. This is a soft goods problem. This is not one you go off and model in your computer. So we've built a 5th scale model, and with a simulated asteroid, it has dynamics associated with it. And we're going to evaluate how we capture it, how we control it, and then working with the crew, how we would access it. So there may be some solutions and specific tools that we may use. We'll have a pretty good understanding of what it'll look like. And as soon as we have a target determined, we'll be able to narrow down the size of the bag. In other words, try to make the bag a little more custom to the particular asteroid, so we don't have so much material to deal with.
And I guess the bag solution is there because there's a lot of different varieties of asteroids. Some of them are solid, metallic, rock-like objects. Some of them are more like rubble piles. Some of them are more like sand piles. So we want to be able to contain that material, and this is the best solution we've come up with to date on how to easily contain that material in a very lightweight fashion. And we think we can probably work through how to get the crew access either with flaps or some way. So we're working through that.
Good questions. Any more? Yep. Go ahead.
Yeah, Mitch Fletcher from Honeywell. In the spirit of all of the things you're doing to deploy existing programs, why the diversion from the CSSS spacesuit?
Yeah, the question was why do we look at using the ACES spacesuit, right? I think is what you're asking, rather than continuing with our exploration spacesuit.
Yeah, so our vision on the spacesuit is not to use this modified ACES, for a long time. We would only use it for one mission. We continue to want to build an exploration suit in partnership with our contractor team, including CSSS. The PLIS may very well be a common component from our exploration suit and this modified ACES technology. So the problem really came down to how we allocate mass within Orion. And when we looked at trying to allocate that mass, it was better, more efficient to use the launch and entry suit as the baseline pressure suit for the EVA. So that's why we made that trade for this initial mission, but certainly down the road, we agree that we ought to go to an exploration spacesuit for planetary or even zero-G type space.
Again, I think, and Steve described earlier in his talk that, we've had 5 neutral buoyancy lab runs with the launch and entry suit. We'll see how that goes through the continual evaluation and see if that makes sense. We may have to do something different. The advantage to us was the launch and entry suit was going to be carried anyway. This is a pretty mass-constrained mission. You can determine that from the fact that Steve's pre-positioning tools out on the robotic spacecraft. So we really didn't have the luxury of carrying a large total new suit there's enough volume for it in Orion. There just wasn't enough mass capability to do that. If we start finding through the NBL runs that this is not the right solution, we'll pursue a different path and go look at some alternate things. We're also open to other suggestions of how we can do things a little bit different in that area. If there's some way that can help us with the packaging constraints and help us with the mass constraints, we'd be open to those. All right, maybe one more question and then we'll call it a session.
What level of characterization is going to be done by the robotic portion so that when the astronauts open up the bag, there's not a big mystery inside? You'll have months to years to do some robotic characterization. What will be done in transit?
Most of the characterization will be done before we capture the object. So, we carry a variety of instruments, optical, LiDAR, infrared, spectrometer. So we'll have it pretty well characterized initially. We'll have a shape model. We'll know what its shape is before we start to capture it. So all of that will play into how we grab it and what its state will be as we start to grab it. We'll be monitoring that. We'll see whether it's a rubble pile, see how well it holds together. One of our current concepts basically uses airbags as cushions, basically, to grab the asteroid. We can do that fairly quickly, and we can apply a very gentle force to it, so we can hopefully keep it in one piece if it is loose. So those are the sort of things we're going to explore with our scale model testing.
Yep, and the other thing I would say too, we've talked a little bit about was when we do the actual capture, we've discussed a concept where we've seen in some of the RFIs where maybe we carry a CubeSat or an observer satellite along with us on the robotic mission. We then deploy that CubeSat close to the capture, so then we can actually have a standoff camera that can actually watch the capture of the asteroid with the robotic spacecraft. And we think that's, again, another area where we can take advantage, because we saw earlier this morning a lot of folks are interested in deep space CubeSats or small little spacecraft. Maybe we could use one of those as an observation platform to actually give us some observation of the capture, which will give us some data about what we have captured and then help us prepare from a crew standpoint that when we actually get it into the distant retrograde orbit, we know what we're going to see when we go inside and look at it. There was one other question on cost, which is folks are always asking about. The Keck study estimated this mission cost around, I think, $2.5 billion or so. We've estimated it without a launch vehicle on the order of about $1 billion. We're still refining those numbers. It depends exactly on the concept. We still have this major decision in front of us. Do we go to a large asteroid, a potentially hazardous one, a couple hundred meters in size and pull a piece off, or do we just go to a smaller one? That will drive a little bit of where we think the cost sits. So we've got quite a bit to look at, but cost is clearly a consideration. We're also leveraging off of a lot of what we're already doing. We were going to do the solar electric propulsion demonstration, so those funds get applied directly to this, so that's not new money, but would be a portion of it. We also have done some things in rendezvous techniques with uncooperative targets through the satellite servicing activity at Goddard. Again, that also leverages into this. So we're trying to take advantage of everything we've been doing already and use those funds. So the new money associated with this should be a lot less than even the numbers I quoted to you here. But before I commit to a number or somebody prints it in some paper somewhere, I think we need to get through the meeting and at the end of September. We need to understand what good concepts we've got, some folks refine some things more, and then maybe by the president's budget request next year in the February timeframe, we'll be ready to talk about a little more certainty where the dollars are. So again, I want to thank you for your time and your attention. Hopefully you learned 3 things about this asteroid mission, right? Number 1 or number 0 is it's not a destination, right? So remember that. It improves our asteroid detection, as Paul talked to you about. It pushes our solar electric propulsion capabilities, which we want to go do, and it provides a tremendous target to develop capabilities and operation techniques for our crews in the future as we go beyond low Earth orbit. So if you can remember those 4 things, you can understand what the asteroid retrieval mission is. Then you need to turn off that logical side of your brain. You need to turn on that emotional, touchy-feely side, the one you never use. And then describe to your friends what you saw in the video at the beginning and jump up and down a few times. If you're able to do it, do a little break dancing back and forth and tell them, we're going to go grab a rock and we're going to move it here. So see you later.
Well, thank you very much. That I think was very illuminating, and it gave us a chance to see how all the puzzle pieces fit together as we leave low Earth orbit and go beyond. Right now, I'd like to invite you over to the exhibit hall for some coffee and a networking break before we start the rest of our afternoon panels. Thank you very much. Excellent. I don't know about the breakdancing.